Welcome back to CS395. This is Nihal speaking, and this is week 4's optional lecture. Since this is an optional lecture, we'll not expect you to know any of the content in this lecture. You will also not have any assignments related to the content in this lecture. In this week's regular lecture, I showed how format string vulnerabilities could be leveraged to write data to pointers that are located on the stack. In this lecture, I'm going to take that a step forward. I'm going to be talking about how you can use format string vulnerabilities to write to almost any location in memory, assuming that you are provided with an input buffer that is located on the stack. So format string vulnerabilities can be used to write data into almost any memory location in certain situations. There are a number of steps that you have to do in order to do this. The very first thing you have to do is figure out where the input buffer is located on the stack. So what that means is if you do something like percent and then a number and then a $sign and P, you should be able to print out the string that is on the stack. You should be able to print out the string that you typed in, and you should be able to see it on the stack. If the input buffer is on the heap, that is, if the programmer used something like malloc to initialize the input buffer, then you will not be able to do this arbitrary memory write technique here. Once we do that, we are going to be able to write to that location in memory. So the way that works is if we take this stack offset right here, and instead of doing $P, if we did $N, we would be able to write to whatever location of memory that we typed into. So if we typed in a memory location right before this, the $sign right here in hex, and then if we use this right here, we would be able to write out memory to that memory location. And this is going to make more sense when you see this in an example. So what we have to do next is we have to select the location of memory that contains data that we have to modify. And this is going to be referred to as the memory address. And the memory address is going to come before the format string vulnerability right here. And then right in between the memory address and the format string, we are going to write an arbitrary number of bytes so that we can write that many number of bytes to the memory location. If you recall, the %n format specifier uses a integer pointer from the stack, and in that integer pointer, it's going to write out the number of bytes that have been written out to the standard output. So what's going to happen is we're going to use this as sort of like our formula for exploiting this vulnerability. We're going to write out the memory address in hex. Then we're going to write out an arbitrary number of bytes. Then we're going to use this format specifier right here. And what this is going to do is it's going to pop this memory address off of the stack, use that as the integer pointer, and it's going to write out the number of bytes that have been written out. All right, so as an example right here, using this formula, let's suppose that we wanted to write this x10 value into this memory address right here. So what we would do is we would first write out the memory address in little endian format. This right here is 4 bytes, and we want to be able to print out 10 to this memory address right here. So we print out another 6 bytes right here just so that we can get it to be equal to 10. And then we specify our format string right here. This is going to pop off the 5th value on the stack. And since we're given that the 5th value on the stack is our address right here, it's going to pop off our address from the stack. Once it does that, it's going to write the number of bytes that have been written out to the standard output. And it's going to write that to this memory address right here. So we are going to be able to control what value is being written out to this memory address right here. We won't actually type out this value right here using the \x right here. We're going to use something like Python that's going to be able to reinterpret these as ASCII characters. So there are certain situations where this exploit does not work. The main situation where it does not work is when pages of memory are marked as non-writable. So when that happens, that means that if you try writing out to a certain page in memory, it's going to deny you permission from doing that. And in these cases, you would have to exploit another vulnerability to allow yourself to mark these memory pages as writable. And the way you could do this is that you could call the function that is responsible for changing the permissions of the pages of memory. But this is a lot more complicated. It requires a lot more low-level knowledge, and I won't be going over how that works today. This also doesn't work if there are null bytes in the memory address that you're trying to modify. So let's say we were trying to modify this memory address right here. The problem with this memory address is that there is a null byte that's located right here in the middle of the address, and that's going to cut off everything that comes right after it. So just be aware of that. If you have a null byte into the memory address that you're modifying, then this will also not work because printf will see that null byte and it will just pretend that everything that comes right after that doesn't exist. So here's a neat little trick you can do to print out an arbitrary number of spaces. Let's say that you had to print out 1,000 characters because you wanted to store the number of 1,000 in a memory location using the %n format specifier. But let's say that your input buffer is a little bit too small for that. Maybe it's only 50 or 100 or something that's way smaller than 1,000. So you can't just send out 1,000 characters before using your %n because your input buffer isn't that long and only 50 of those characters will actually be read. So the solution to this problem is to use this format specifier right here. This is the alignment format specifier. And what it will do is it will print out a pointer that's on the stack. But before printing out that pointer, it's going to print out a certain number of spaces so that the total number of characters that have been written out using this format specifier is 1,000 characters. So if the pointer is, let's say, 10 bytes of memory, we have 2 bytes for the 0x that comes before the pointer, and then 8 bytes of the pointer itself. Then it's going to print out 990 spaces right before that so that it gets aligned to 1,000 characters. And that way you print out exactly 1,000 characters. So just an example of how this works. Let's say you create a test file that looks like this, and you set this integer n equal to 0. What we're going to do here is we're going to use that format specifier that I just mentioned earlier, but we're going to use 100 instead of 1,000 because I didn't want 1,000 spaces to be printed out. And we're going to use the %n format specifier to print out the number of characters that have been written out to the integer. And we're going to use the address of n both times here. Then we're going to print out the value of n. What you can see right here is n is equal to 100. So that means 100 characters in total have been printed out by this line of code right here. And when you look at what's actually printed out, you see a bunch of spaces followed by the pointer at the end. So this is going to be exactly equal to 100 because we specified 100 here. And it's going to make sure that it's aligned however you specify it so that n becomes the exact number that you would like it to be. So this is how we can have more exact influence over how we can, I guess, print out an exact number of characters, even if our input buffer isn't that long. So I am now going to be showing you the coins program. This is the program that we're going to be exploiting today. When we execute the coins program, it asks us to type in our name. So I'm going to do that. It says, hello, Nihal, you currently have 10 gold coins. Sorry, you're not rich enough. So if I use the file command here to show information about the coins executable, you'll notice that it's a 32-bit executable instead of our typical 64-bit executable. The reason I compiled this as a 32-bit executable instead of a 64-bit format is because that makes it less likely to contain nulls in the address, because the address that we're using, the address space that we're using is going to be smaller than the 64-bit addresses. All right, so the next thing that we're going to do is we're going to open up this file in Ghidra. So I'm going to create a new project. Do that. I'm going to add the coins binary to that file, to that project, I mean. Double click on it, get the little dragon pop up. Hit yes for analysis. Now I'm going to go into the functions tab here, and I'm going to find the main function. So this is the main function right here. And as you can see, the first thing that happens is we are given this undefined local here, and we are also given a car array of 50 bytes. Ignore this this little thing right here. This isn't relevant to what we're doing right now. But once we create this character array, we're going to print out our name, and then we're going to fgets 50 bytes into this this variable right here. So since we know that it's asking for our name, and since we know that right after that it is saving our name into this variable, I'm going to name this as name, because this variable is a car array that contains our name. Once we do that, we're going to send that car array into a function called checkCoins. So let's double click on that and see what it looks like. Over here, we know that the parameter is going to be our name, so I'm just going to rename this to name. What happens here is it prints out hello, and then we see that this is vulnerable to a format string vulnerability because it's directly printing out our name right here. We set this local variable here called ivar1 equal to coins. And then it says you currently have %d gold coins, and it prints out the number of coins that we have. If the number of coins that we have is less than 1,000, it prints out, sorry, you're not rich enough. Else it will print out, congratulations, you're rich. So this coins variable, if we just go to the assembly and then double click on the coins variable, we can see where it's stored. This is a global variable. And I just show you right here, it's initialized to 0A000000, which is going to come out as 10. And this is stored in little endian format. So this is actually the lowest byte, not the highest byte. So it's this coins value is initialized to 10. And it is a global variable. And what we have to do is we have to make it so that we get this line printed out instead of this line. So what we want is we want coins to be greater than or equal to 1,000. So what we have to do here is in order to print out the congratulations page, we need to have more than 10 gold coins. We need to find the memory location that contains the number of gold coins we have. And we need to overwrite that value with 1,000. So that way we'll have 1,000 gold coins instead of just having 10. And we can exploit the format string vulnerability that occurs when the program prints out our name. And we can use this vulnerability to change the number of gold coins that we have. And that is what I'm about to show you. So the very first thing that we're going to do is we're going to go back to our code right here. And we're just going to execute this program again. But this time, instead of typing in our name, we are going to send in a bunch of %p values, like so. And this is going to leak out values that are on the stack. What you're going to see is that you're going to see that eventually we hit these values that say 7025 E2, 7025 E2. And if we had a buffer size that was greater than 50, we would see this being printed out even more times. This is going to be repeated multiple times because this is actually the start of our string. 25 represents, I believe, the % sign in ASCII. 70 is P in ASCII, and 2E is the period in ASCII. So this is actually where our string is beginning right here. And it just keeps on going on and on and on. It's stored on the stack. Our string is stored on the stack. And what we have to do is we have to figure out where exactly on the stack is our string located. So the way we do this is we just count up how many values are on the stack before our string starts occurring. So we count it up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So this right here is the 15th value on the stack. And what we're going to do is we are going to be sending BBBB percent $15 $P. If we have control over this value on the stack right here, then it's going to print out hex 42424242 because 42 is the ASCII code for B. But unfortunately, it's only going to print out 2 42s. It's not going to fill up the entire thing with 42s. What we want is we want to have an address that allows us complete control over the address. We want an offset that gives us complete control over the address. So what we're going to do is we're going to use the next offset over. So instead of using 15, we're going to try using 16 this time. And we'll add some more characters here just so that we can see what happens. So over here, when we print out the 16th value on the stack, we get 43434242. So these lower end bytes right here, these BBs are coming right here, and the Cs are coming right after that. So it looks like these 4 bytes that are right here, these the CCBB, this is what controls the 16th value on the stack. And what we want is we want to have complete control over that. So we know that we need to offset it by 2 bytes so that we can get to these 4 bytes. So we're going to write AA, then we're going to write BBBB, percent $16 $P. And now we've shown that we have complete control over this address. If we change this address to something other than B's, like if we use C's or if we used an actual memory address, then it would print out that actual memory address. And what we could do is we could write AA and then our memory address instead of the B's. Then when we do the percent $16 it's actually going to write memory to this address right here. It's going to write memory to whatever this address right here is. It's going to segfault because this memory address probably doesn't exist. But this way we are able to write to whatever memory address we would like. Since we have control over these BB values, we have control over what gets printed out here, or the pointer that's on the stack at the 16th value. What's going to happen when we replace it with N is this gets popped off of the stack right here, and we write to that address the number of characters that have been printed out. So what we have to do now is we have to find the memory address that contains the number of gold coins that we have. And we can use a debugger to search for this address. What we'll do is we'll set a breakpoint in the check coins function right before the 3rd printf statement occurs. If you recall, in Ghidra, we saw that the 3rd printf is where we actually print out the number of gold coins that there are. So if we set a breakpoint right before this 3rd printf occurs, we will be able to see where exactly which address it's loading when it uses that printf statement. And this is our target address. This is the address that we want to modify. We're going to change that address from 10 to being 1,000. We'll have to disable ASLR for this part because ASLR will randomize the memory addresses that are being used, and we don't want that to be hurting our exploit. The memory addresses that I'm going to be using will still probably be different than the memory addresses that you'll have on your computer if you're following along. So please don't just copy and paste the addresses that I found. Maybe the addresses will be the same, but they could also be different as well. So just keep that in mind. If something in your exploit isn't working, then recheck your addresses and make sure that you're using your correct addresses for your system and not for my system. All right, so I am going to open up our debugger real quick. I'm going to, first, I'm going to just show you the disassembly of check coins. So right here, we have our 3 printf statements, and the third printf statement is the one that actually prints out the number of coins that we have. If you notice, there are 2 things being pushed onto the stack here. So I'm going to set a breakpoint right before this EAX value gets pushed onto the stack. So that's going to be this check coins plus 56. So I will set a breakpoint at that value. And then I'm going to run the program until we hit that value, or sorry, until we hit that address. So right here, what's happened is if we look at EAX, we can see that EAX is set equal to 10. If that means that EAX currently contains the number of coins that are in our that we have, and right after that we push EAX. So this is clearly the value that's going to be used for the format string that's there. It's going to be the value that's going to be printed out. If we look down here in the code, we see that there's this something that's being moved into EAX. This is most likely the address of the that contains the number of coins that we have. So what's happening here is we're adding hex 24 to EVX. We dereference whatever that value is, and we store the dereference value in EAX. If we just look at what EBX is right now, we see that it's this value right here. And if we add 24 to that, so if we copy that and add hex 24 to that, we're just going to have that. So this address right here is most likely the memory address that contains the number of coins that we have. And to confirm this, we can use the examine command to examine that memory. And as you can see right here, we see that it has a value of 10 inside of that memory for 10 coins. So we have confirmed that this is the memory address that we want to be using. So the very next thing that I'm going to be showing you is the exploit itself. First, I'm going to type out the entire exploit, and then I'm going to explain how it works. All right, so the way that this exploit works is we are using the sysstdout buffer write function. What this does is it's the same thing as print, but print can be a little bit glitchy when it comes to hex characters, which is why I use this function instead of print. The next part of this is recall that earlier we did something like AABBBB $16 If you remember that, that's the same thing that we're doing here, except instead of the B's, we're replacing the B's with the address of the value that we want to change. Right here, we use %994p to print out 994 characters out, because so far this is 6 characters being printed out, and we need another 994 characters to get it to be exactly 1,000 characters. And then to modify that address, we use $16 $N, and this is what allows us to become rich. So this is what gives us that prompt to pop up. So if I go back to the slides, right here is just another explanation for how this works. So we know that the input on the stack is being pushed on the 16th offset. We pop off the value that's at the 16th offset, which is our memory address right here. And we are now able to write to that memory address. And that is what basically allows us to exploit this program. So that is all that I have for you today. One more thing that I just wanted to go over was this very interesting paper that I found from Stanford that explains all of the different things that you could be doing with format string vulnerabilities. If you scroll through, it's a very long paper, but it explains a lot of different techniques that format string vulnerabilities allow you to do. And it explains how format string vulnerabilities work from a high level perspective. You don't have to read this paper. You don't have to read this entire paper. I just thought it was an interesting paper and I just wanted to share it all with you. But that is all that I have for this optional lecture. So have a good day, guys.